Happy birthday, everyone. It's the 50th anniversary, so that's kind of cool. So today we're just going to tie up some loose ends with this whole magnetic theory thing and right-hand rule and all that good stuff, and torques and forces and lines and titers and bears, oh my. So the lecture will take pretty long, kind of wrap up some solenoid stuff, some torque, and then I'll send out the assignment with the answer key for that, and so we'll call it a day. So like I said, it's a rainy Earth Day, but I'm back in the element, and yes, I know there is like a stain on the back of my shirt. I had a pin explode in the dryer. It was ugly. Anyway, so all right. So let's talk about solenoids, because solenoids are pretty important. They actually act as like actuators to make things move. Okay, so as an example of that, and this is what we're talking about. So here I've got a solenoid, right? And I've got a bar that I'll put in there, and I grade duct tape that to a Newton scale so you can see how much force there actually is. And so what this equation gives you that I have up here, B equals mu naught I N over L, gives you the strength of the magnetic field that's inside that solenoid. So this is just the strength of the magnetic field, not the force, but we're going to look at that. So vacuum permittivity constant, I is your current, N is the number of turns, L is the length. So if you think about it, that makes sense. So as the length becomes longer and you spread that out, the magnetic field within that solenoid is going to become less. But if you have more turns and you have more wire wrapped around it, then that's going to make that magnetic field become stronger. And if you put more and more current through it, that creates a stronger and stronger magnetic field as well. So we'll crank this up, okay? And we'll start with, I don't know, about 1 amp, okay? And so if I put this in here, okay, and then try and pull that bar out, it takes about 1 Newton of force to pull that out. I have a current, I got a pretty strong magnetic field, this thing's turning into a magnet as well. So then, if I crank that up to say 2 amps, okay, then when I go to pull that out, oddly enough, now I'm up to about 2 newtons of force to pull that metal rod out of that loop. Okay, let me make sure you can see that. Okay, so now I'm up to about 2 newtons. So true of anything, if you're going to do anything, go big or go home. So if I crank this thing all the way up to about 4 amps, okay, so now, like even if I just get this thing close and let go of it, whoop, okay, make sure you can see that. So if I get it close and let go, it just pulls it right in. So now, I've knocked off one of my, hold on, I have technical failure. Rats, hold on. Okay, so now to pull that out, I'm up to over 5 newtons of force to pull that thing out. So as the magnetic field becomes stronger, you have more and more, or as the current becomes stronger, you have a stronger and stronger magnetic field, you have a lot of wires wrapped around it, and this would be like the length of the solenoid. Okay, so let's talk the right-hand rule and torque. So let's say that I have a wire like this, okay, and I'm going to put that in so the wire's like this, okay, and this is really important. So it has this side A, and this side is B. It's just generic A and B. It doesn't make any difference which one's longer, which one's shorter. It doesn't make any difference. But it is going to be important in terms of how we keep track of what's what. And I've got a magnetic field coming across like this, okay? So I'm like this, the magnetic field is coming across like this, and this thing can pivot in the middle like this, okay? So I've got a little wire, this thing is spinning like so. So what I want to do is calculate the total amount of torque that's on it. Well, to do that, I got to figure out what's happening with which direction the force is acting. So if we start with over here, okay, the current, because this is the harder one. So the current's coming down like this, so I put my thumb down. Then the magnetic field is going across like this. So I've got my hand going down like this. The magnetic field is pointing in this direction. So this is going to the force on this side over here is going to be out of the page. So this side over here is going to tend to pull this out of the page. Now, this side over here, where I've got the current going in this direction, and I point my finger in the direction of the magnetic field, then my fingers point into the page. So this one over here is turning this into the page. So I've got this loop, this side's pulling it out, and I've got this side pulling it in. Okay, so I'm going like this, right? So I got this action going. Okay, so this side's coming out, this side's coming in, and it's just going to make this thing spin like this, right? Just like I did with the battery and copper wire. Now, so the whole key to this is also going to be this dimension. So since torque, remember, is equal to force times that radius. So the force is going to be what's going to be coming from the magnetic field and that interaction with the charged particles. The radius is going to be the distance from the center out to the edge, which is going to be half of b. So doing some nifty little algebra here, okay? So torque equals force times radius. Okay. Well, the force is going to be Bill. B is going to be the magnetic field. I is going to be the current that's moving in that. L is going to be the length, and this is going to be important. L is going to be the length that's being subjected to the magnetic field. So when you look at how this deal is going to play out, the way this is drawn, this dimension A, and listen to me, listen to me, listen to me, listen to me. This is going to be important when we get into chapter 25. That length isn't this side, because this side isn't being interacted with the magnetic field. This is the side that's being interacted with the magnetic field. So when you're using that value of L, listen to me, I beg of you, please. Use the length that's being subjected to the force in the magnetic field. This side here has nothing to do with it. Okay? This has nothing to do with it. It's only this side here that's being subjected to that force, because those are the particles that are feeling. Once it gets here, they don't feel anything, because then it's going parallel with that magnetic field. Okay. So, here's what we got, kids. So we've got Bill times R. So L is going to be A, because that's going to be this dimension here. So this is going to be this A dimension here. I got B over 2 because it's going to spin about that center axis. Okay, so it's going to spin around like this. So that's going to be B over 2. Now, because both sides are feeling that force, okay, it isn't just one side. Both sides are feeling that force, and they're both going in that same direction. Both are making it spin. So I'm going to multiply this by 2. Well, this gets a little bit clever, because then, once I multiply this by 2, that cancels out, so I have A times B. Well, A times B is just the area of the loop, okay, because it's dimension A times dimension B, and oddly enough, that works out to be then, sorry, hold on, gravity sword. Here we go. So this side over here works out to be like meters squared, all right? So you can just write this as area. So if it happens to be like a square, okay, so let's say this is a perfect square, then it would just be like, 5 meters squared. Now, when you look at this, and this is going to be playing out in some of your problems, remember that torque can equal a couple of things. Torque can equal force times radius. It can also equal I alpha. Oddly enough, this thing has a moment of inertia, right? Not much, it's a little thin wire, but it has a certain moment of inertia. So you might want to consider this when you get to some of the problems on the assignment. So if you have, let me jump back up into here. If you have, this is just if it was one loop, if I had like 4 or 5 of these wires around like this, then however many loops I'd have, I'd multiply that by n, okay? So this would be n times a times, okay? That's going to be that cross-section area. So keep that in mind when you look at some of the problems. On the assignment, and I know I'm giving you the answer key, but I want to make sure everybody kind of gets, it'll be problem number 8. This is kind of, you have to kind of think through what's going to happen on number 8. It'll make sense when you get this, but you have a current of 2.5 amps going this way, and you have a thin hoop down here, and you want to talk about the force, okay? So with this one, you're really not talking about torque, but since this is going in this direction, and you want to find the loop that stems in, blah, 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 okay? So what you want to look at when you get to this one, it'll make sense. You're going to have 2 different forces acting on the top and bottom of the wire. So when you get to that, one of those is going to be attractive, one of those is going to be repulsive. So what you're told, and I got to remember which direction I have the current going. So yeah, so this one is going to have this is also going to have a 2.5 current amp going. Current. Why do I not have that on? Oh, I do have that on both of them. So you got that going this way. So this is going to boil down to a problem of wires. So remember, these right here have the same direction. So those have the same direction. So you got to think through, wow, is that repulsive or attractive? Down here, it's going to be in opposite directions, but you're going to have a different dimension. So that's kind of one of the more difficult ones to think through. Okay, that's it. Happy Earth Day. Be thankful. You know, you all have been my AP Physics class. I gotta keep track. You all have been very supportive of the solar project, and I appreciate that. It was an honor to have, I'll have that AP Physics 4th block up there. So anyway, happy Earth Day, and I'll get this stuff sent out. Thanks.